Can you see my screen?
Yes, sir.
Okay, thank you. Okay, so as I mentioned in the last class that today I will take half an hour extra. So that means today we'll have a class from 3:30 to 5:30. So half an hour extra. So those who have some other class at 5 o'clock, they may leave and they can look at the recording. And if they have any doubt, they can look at the recording as well as the PDF lectures. And if they have any doubt, then they can ask in the next lecture. All right. So far we have learned about norms, matrix norm, and we have seen their usefulness in several other things, many ways to define norms and why norms are useful. Several things we have discussed about norms. And then we have also learned what is spectral radius, how it is closely related to the norm. So a few things we have already discussed about norm. Now, today in in today's lecture, my plan is to introduce or to start a new section like matrix factorization. I had mentioned earlier also. So like we have several, you already know some of the factorizations. So what is a matrix factorization? Matrix factorization is like when you factorize a matrix in terms of as a product of different matrices. Okay, some other matrices. So if suppose you have a matrix A, then uh, can you write it in some way or as a product of 2 or 3 matrices? Then it is called matrix factorization. There are several matrix factorizations available, and they have their advantage over each other. But before we start matrix factorization, I just want to mention one more definition in norm. Just 2 minutes, and then we will start this matrix factorization, because I don't want to leave that thing for some other part. So it is called unitarily invariant norm. So a norm, when a norm is called unitarily invariant, if it is called unitarily invariant when it satisfies one property. So what is that? It is like when you multiply with a unitary matrix from left hand side or right hand side, then the norm doesn't change. So then it is called unitarily invariant. Okay. So a matrix, so I'll just give the definition and 2 examples, but you can verify that those examples are like those norms are unitarily invariant. And then we will start matrix factorization. So just one definition to start with. It is uh, it is remaining from the previous lecture. Unitarily invariant norm. So what it is? So a norm on on this space of matrices is called unitarily invariant if norm of UAV is equal to norm of A for all A matrix A of size n cross n and unitary matrices U and V size n cross n. Okay, these two are unitary. Okay, you know what is a unitary matrix. We will define unitary matrix and talk more about unitary matrices in today's lecture. But for the time being, I assume that you know what is a unitary matrix. A matrix is called unitary if U star U is identity. Okay, so if a norm satisfies this condition, that means norm of UAV is equal to norm of A for any given matrix A and unitary matrices U and V, then it is called unitarily invariant. And examples of unitarily invariant norms, there are many norms, but the 2 most useful norms are unitarily invariant. They are operator 2 norm. So this is operator 2 norm. It's very easy to verify why it is unitarily invariant. What is operator 2 norm? You know, it is like this one. Okay. And Frobenius norm. What is Frobenius norm? So if A is denoted by Aij, then the Frobenius norm, it's basically the L2 norm on a space of matrices. That means you take the uh, you take this sum over all ij and take the square root of this sum. So basically, this is nothing but trace of a star, or you can say a star a. It's the same thing. So this is the Frobenius norm, and using the trace property, you can easily verify that um, Frobenius norm is also a unitarity invariant. Okay, so we will use this fact actually in today's lecture. That's why I have introduced it here. So now we start new section. It is matrix factorization. So as I mentioned that there are several matrix factorizations available, and they have their own advantage. Some of the matrix factorization we will consider or we will discuss in this course. But before I start, can you recall or can you tell me if you remember a few matrix factorizations? Can you just name what matrix factorizations you have learned so far or you can recall? So matrix factorization means you have a matrix A of let's say for simplicity assume that A is of size n cross n. Then if you can factor this factorize this A in terms of like as a product of two matrices or three matrices, depending on what is your factorization. So can you name a few factorization for a matrix? I'm sure that you have learned quite a few matrix factorizations already. But can you name them?
The product of upper into lower
So LU factorization, you mean?
value
Okay.
factorization. Then it says
This is
Cholesky factorization. Then
Cholesky factorization. What is Cholesky factorization?
I guess into upper or lower into lower
So
matrix.
it's yeah, it's something like this kind of thing. Okay. So you know LU factorization, or at least you have learned. We will discuss some of them in this course. And you are saying the Cholesky. Okay. What else?
Like diagonalization one, like but that's restricted to
Yes. It's this diagonalization. If the matrix is diagonalizable, then so I'm not saying that for every matrix you can find this factorization, but at least under certain condition on a matrix A, you have learned this kind of factorization. So like you have this diagonalization. This is called as eigenvalue decomposition. Why this is called eigenvalue decomposition? Because the diagonal matrix gives you the eigenvalues, and this transformation matrix S, this gives you the eigenvectors, corresponding eigenvectors. What else?
the one we discussed lemma. It's like that kind of factorization.
Which one?
The one we got from like Skur's lemma that
Huh.
any matrix
Yes.
use
So
to
what is
give
that? Yeah. So a
like
matrix.
one.
Yes. So it is like something like this. Right? So it's like every matrix is, or every complex matrix is upper triangularizable. So where U is unitary and T is an upper triangular. So it's the Schur's lemma, or you can say Schur's factorization. What else? So we have already listed quite a few here: LU decomposition, then Cholesky, eigenvalue decomposition, Schur's lemma,
Singular value decomposition also like
singular value decomposition. That means a matrix can be written in this form, where U and V are unitary matrices, and sigma is a diagonal matrix with non-negative diagonal entries, and the diagonal entries are arranged in descending order. So this is SVD, singular value decomposition. What else? Anybody else or any other factorization? So from this SVD, you can also write polar decomposition. Have you heard about polar decomposition? It's like every or a matrix can be factorized into in this kind of decomposition where P is semi-definite and U is unitary. So it's like polar decomposition. Then there is another one which is QR decomposition. QR decomposition. So what is QR? Q is unitary and R is upper triangular. So this is QR decomposition. So we have already listed. You can see that some of them are very useful in applications, and we will discuss them in detail in this course. Like the most important factorization from application or from practical point of view, all have their own advantage. Some of them have their theoretical advantage, some of them have their like um, like practical advantages, but the most useful factorization is Schur's lemma here, Schur's decomposition, because using this we can do several things. You will see this SVD is another one. SVD also one of the most important or useful factorization. Then this polar decomposition follows from SVD. Then this QR decomposition is also very important in application. In fact, these two things, they are useful. These two results are useful in finding eigenvalues of a matrix from practical point of view. We'll discuss briefly. I'm just giving you some. I'm just recalling what you have learned so far. There is another decomposition which you might have learned. It is called Jordan, or at least you have heard Jordan canonical form, right? So if you have a complex matrix A, then you can write it in terms of this. So every matrix is similar to it's a Jordan form. So Jordan matrix has certain structure. We will discuss this. So this is Jordan matrix, Jordan canonical form. Then you know that there are spectral theorem for unitary and for normal matrices or for Hermitian matrices, that these matrices are unitarily diagonalizable. So this kind of factorization you have already learned here. So in this course, I won't discuss this. This is a basic basic factorization. I won't discuss. Cholesky also, it's a particular case of this LU here. I will discuss mainly these decompositions here. So some of them are new for you, like SVD. We will discuss in detail. We will discuss this Jordan canonical form also, and Schur's lemma is also since one of the most important especially in stabilizing or establishing other results. So we will discuss Schur's lemma also in more detail. Okay. Okay. So let us start what you already know about matrices, and then we will gradually develop on these things. So let us start by recalling what is a diagonalization. What is a When do we call a matrix is that a matrix is diagonalizable? So what do you understand by diagonalization? So let us recall this thing first, and then we will discuss more on this factorization one by one. We will conclude this section in 4-5 lectures. So it will take time, but we will slowly develop a nice theory on this. All right, so let us define what is the diagonalizable matrix. So I'm just recalling. You already know this. I won't discuss these things in detail, which you have already learned. I'll introduce new things here. But these terms I know, so I will just set up the terminology here so that I can use the same terminology throughout the course. So what is the diagonalizable matrix? What is a diagonalizable matrix? So suppose that we have a matrix A of size n cross n over the field F. Okay. Then where F is either R or C, then A is called diagonalizable. A is called diagonalizable if there exists an invertible matrix P of size of the same size of the same field such that P inverse AP is diagonal. Then we call A as diagonalizable. Then we say that A is diagonalizable. So basically, if A is similar to a diagonal matrix, then A is diagonalizable. So what we know is that not I'll just recall again. Not every matrix is diagonalizable. Why it's not diagonalizable? Because you can take this example here. There are many examples. So this simple example here you can take. This is when you consider this matrix over R. Then this matrix has only two complex eigenvalues. So this cannot be. This matrix is not diagonalizable when you look at this matrix over the field R. But the same matrix, if you look at over the field of C or field of complex numbers, then it is diagonalizable. Similarly, if you look at this matrix, let's say this one, then this matrix, if you look at over C, then this matrix is again not diagonalizable. So there are several examples you can construct. So not every matrix is diagonalizable. So there are certain conditions or equivalent conditions under which you can say that a matrix is diagonalizable. For example, one standard result is that a matrix is diagonalizable if and only if there exists a basis of Fn. So if A is of size n cross n, if there exists a basis of Fn consisting of eigenvectors of A. So this is one of the main like characterization for diagonalizable matrices. But then there are several equivalent characterization to say whether or to check whether a given matrix is diagonalizable or not. So let's say if we have a matrix A or F, then A is diagonalizable if and only if there exists a basis of Fn consisting of eigenvectors of A. Okay. So if you can find a complete set of eigenvectors for this matrix A, then using those eigenvectors, you can construct this transformation matrix P here. And then you can write P inverse AP as a diagonal matrix. So I'm not going to prove this. This you have already learned. So this is for diagonal for diagonalizable matrices. Now, since we know that not every matrix is diagonalizable, then what else we can say? Okay, or can we, if we try to like rephrase this statement or like modify this statement, then you can say like, okay, not every matrix is diagonalizable. So that means not every matrix is similar to a diagonal matrix. But then can we say that, okay, if not if not similar to diagonal, then can we say that if it is similar to a upper triangular matrix or lower triangular matrix? The answer is yes. If you have if the field is the field of complex numbers, so that means if you have a complex matrix of size n cross n, then you can say that this matrix is upper triangularizable. You can say that means there exists a matrix, invertible matrix P, such that P inverse AP is upper triangular. So what I'm saying is that not every matrix is diagonalizable, but you can say that every square. So, or you can say that if so, let A be n cross n matrix over C. Okay, then it is. Then you can say then there exists invertible P such that P inverse AP is upper triangular. Okay, so okay, this result is very powerful because it says that every matrix A on C or over C is upper triangularizable. That means it's similar to an upper triangular matrix. Using this result, you can prove several other things, like you can prove that sum of eigenvalues is the trace, or product of eigenvalues is the determinant of a matrix. Several of these kind of results you can prove. Okay, but we are basically interested. So therefore, this kind of transformations, like similarity transformation, that means when we using this, so if we have this kind of thing, let's say B inverse AP, then you can say that okay, A is similar to B, or you can say that when we apply this transformation P on A, so this kind of transformation is called similarity transformation. That means you apply P inverse from left hand side and P from right hand side. So you can say that when you apply similarity transformation uh, on A using this matrix P, then you get B. So this kind of transformations are very useful. At least in theory, you can see that uh, because similar matrices preserve like nice properties. There are several properties which are same for a similar matrix, and also the if you define this similarity, if you define a relation on space of matrices using similar matrices, like two matrices are related if and only if they are similar, then this relation is an equivalence relation on space of matrices. So basically that means it gives you a partition of the set of all matrices. So every equivalence relation gives you a partition of the set, or you can say that it partitions the set into equivalence classes, into disjoint equivalence classes. Now, this kind of transformations has certain advantages, but there are also several drawbacks. We will see that, and therefore we want to achieve a similar thing, but what the problem in this is like not in theoretically there is no problem in saying that A is similar to B, or having this kind of transformation, because they simplify many things. But we can further like say something more, or we can ask for like something extra than this. It is like it will be called unitarily similarity transformation. That means this P matrix would be replaced by a unitary matrix. Now the problem here is that in like when you try to use similar this result, like P inverse AP, if you want to use, or let's say this result if you want to use here in order to find eigenvalues of a matrix, because this result says that every matrix is similar to upper triangular matrix, and for upper triangular matrix we know what are the eigenvalues. They are nothing but the diagonal entries. So in theory, it is easy to say what are the eigenvalues of A. You can say that okay, since it is a complex matrix A, we know that because of this result, we know that this matrix is similar to an upper triangular matrix T. So just look at the diagonal entries of this matrix, and they are the eigenvalues. But then there are problems like how to find this P, that is not known, because usually this P is found by knowing the eigenvalues and eigenvectors. So if you know the eigenvectors, then you can construct this P, and then you can write this decomposition. But in general, that is not available. That is what you are trying to do. So first thing, that this decomposition is written using the eigenvalues and eigenvectors. So that is not known to us. And finding eigenvectors is a difficult job. It's like you cannot do it if the matrix is of size greater than equal to 5. So that is a like not for every matrix of greater than equal size greater than equal to 5. You cannot say exactly what are the eigenvalues. You just need some like approximation, or some algorithm to find the eigenvalues. Okay. And the second disadvantage of this is that okay, even if we if we don't know this P inverse or P matrix, this transformation matrix P here, then we can say okay, this suggests us something like some algorithm to find this. So it says that okay, you don't construct this P, or you don't have this P at the beginning, but you try to find, like let's say uh, P naught, P1, and so on. You try to find this matrix P using some kind of like iterations, and iteratively you find these iterations in such a way that this pk, as k tends to infinity, this pk uh, like converges to a p such that p inverse ap, such that p inverse ap is upper triangular, something like that. So it suggests us some algorithm that you don't consider like we don't have p, but we can like somehow try to find a sequence of matrices that converges to p, where p is such that p inverse ap is upper triangular. But then there are other problems, like in this kind of transformation, this inverse is involved. So finding inverse of matrix is again not easy. Not easy means it's like it's a it's a very sensitive process, because if the matrix is like if the, let's say, we know that all eigenvalues of an invertible matrices are non-zero. So non-zero means even if it is close to zero, that means let's say it's of small magnitude, let's say 10 to the power minus 16, then it is, in theory it is non-zero, but in practice it is like it is considered as zero, like it's close to zero, very close to zero. So if you try to divide something by this kind of number, then it introduces like large errors in your computation. And then if you don't bound these errors, then whatever results you get at the end from your algorithm, that may not be may not be acceptable to you. So this kind of problem is also there. So this process is not much of practical use, using or finding p such that p inverse ap is upper triangular, something like that, in order to find eigenvalues. But in place of this, if we somehow somehow get this kind of thing by using a transformation which we will replace by a unitary matrix. So if we achieve similar thing with a different p, that p has some extra structure such that it does not like amplify the errors, and it also keeps everything in a nice like in the nice structure, then that we can use, and that is actually achieved by Schur's lemma. But before that, we will with this motivation, we can start today's lecture by introducing unitary matrix. Okay, so I said many things, but it is just to make you like realize that we already know few factorizations, few things we already know. Why do we need new things? So I just want to emphasize on like every factorization, everything has its own advantages. So we start with unitary matrix, and then we will introduce Schur's lemma, and then we will look at how like useful this result in solving many other things. Okay, so let us start by introducing what is a unitary matrix. So you know what is a unitary matrix? A matrix U of size n cross n C is called unitary if U star U is identity, or you can say same thing, that U star is identity. Okay. If in addition, if U is an n cross n matrix over R, so that means when you consider the underlying field as the field of real numbers, then if U is in this, then U is called real orthogonal, if U transpose U is identity. It's the same thing. So if the field is the field of complex number, then it is called unitary. Otherwise, it is called real orthogonal. Okay. Now let us consider the same similarity transformation which we have seen. Now from this U star U, you can easily see that U star U is equal to I. This implies that inverse of U is nothing but U star. So if you want to replace your, or if you want to achieve similarity transformation via unitary matrix, then your like this transformation will be of the form U star AU. Right? So it's again a similarity transformation, because U star is nothing but U inverse. But now this transformation, which we will call as unitarily similarity transformation, these transformation have certain advantages over the usual similarity transformation, and therefore in the following, like in the Shor's lemma or in the QR algorithm or in some other factorization, we will see that instead of finding factorization using a similarity transformation, we will try to achieve that factorization via unitarily similarity transformation. Now you can say, what are the advantages? Okay, so let us look at what is the advantage if we, instead of an invertible matrix, we have a unitary matrix. Instead of having just a invertible matrix, if we have a unitary matrix, then there are certain things. First of all, you can see, or let me write this as just for your records, I will write it here. So as advantages of unitary transformation or unitary similarity transformation. So first of all, you know that since if U is unitary, then U star is just U inverse. Okay, so having unitary means if you have a unitary matrix, then finding inverse is very easy because you just take the complex conjugate transpose. So it is immediate. So if you know the matrix, then you know its inverse also. If the matrix is U star, is matrix is unitary. Not only that, if you take the product of unitary matrices, then it is again unitary. So product of unitary matrices is again unitary. So that is also fine. Not only that, if you apply unitary matrix on a vector, then this like transformation preserves the angle as well as length. What does it mean? It means that if suppose you have two vectors x and y, let's say in C, and if u is unitary, then the angle between x and y is same as the angle between ux and uy. So what is angle between x and y? It is y star x. That means the inner product of x and y with respect to the standard inner product. And here also it would be uy star ux, but then it is nothing but y star u star ux, but u star u is identity, so it is just y star x. So they preserve the angle, and also they preserve the length. That means if you have this, then it is same as this. So this is the like 2 norm of x. It is same as the 2 norm of ux. Right? So the unitary transformation preserves angle as well as this. Not only that, if you apply unitary transformation on a matrix, then this transformation does not amplify the errors which are available in the matrix. That means if the matrix has certain error, then after the transformation also the matrix will remain have the error of same magnitude. So it will not amplify the error, and that is a big advantage of having unitary transformation, because in the numerical algorithms it will not introduce more errors. So the errors which are already there, they will be there, but because of use of this transformation, we will not add any extra error in the algorithm or in the like computation. Why this is? Because generally these errors and these are like subject to how sensitive your problem is. So the sensitivity of a problem is like is measured by condition numbers. So I don't know whether you have heard about this or not. I'm just telling you, you don't have to like much worried about this thing, just for your knowledge. So if suppose you have a matrix, so if suppose something is involved, like for some problem you are solving involving a matrix, like solving a system of equation or solving a least square problem or computing or solving an eigenvalue problem. Okay? So wherever some matrix is involved. Now, if the matrix is involved, then how sensitive that matrix is with respect to the perturbation. That means if you change slightly the entries of matrix, slightly means if you just give some perturbation to this matrix A, then how the output changes. This measure is actually measured by condition number. So if suppose the change in the output is small with respect to change in the input, then the problem is called well condition. And if the change in the output is large corresponding to small change in the input, then it is called ill condition. Okay, and this conditioning is measured by condition number. For example, for a matrix, the condition number of an invertible matrix is denoted by, generally it is denoted by this kappa A, and uh, if you specify some norm also, then it is like this. So it is with respect to some norm. And what is this? It is just the product of these two norms, product of norm of A and norm of A inverse. Now, if this condition number is small, then the matrix is like less sensitive to the perturbation. And if if this condition number is large, then it is highly sensitive to the perturbation. Highly sensitive means if you change slightly in the input, the output will drastically change. Okay. Now, if suppose your matrix is a unitary matrix is invertible. So if U is unitary, then you can easily find, like for example, if you look at this uh, condition number of A with respect, or condition number of U with respect to two norm, operator 2 norm, then it is easy to see that it is nothing but 1. The condition number of U with respect to 2 norm, that means this is 1. Why this is? Because 2 norm of U is 1. And since you know that all the norms are equivalent, so actually whatever norm you take, this matrix remains well conditioned. Okay. Now, so therefore, now if you look at, if you now use this unitary matrix in a for the similarity transformation, that means suppose that A is obtained by applying unitarily similarity transformation on B by using this matrix U. Then clearly you can see that the operator 2 norm of A, this is operator 2 norm of A is same as operator 2 norm of B. Why? Because 2 norm is unitarily invariant. So you see that even after applying this similarity transformation, the norm remains same. And therefore you can see that the condition number of A is same as condition number of B. So that means even after whatever be the error was there in the matrix B, it remains the same after this similarity transformation also via this unitary matrix. The error is not changed. It is exactly same. So even after the transformation, we are not adding any more error in the computation. Or you can say that, in other words, you can say that if suppose we perturb B slightly, then the resulting perturbation is, so if suppose A is, let's say, U star BU, okay, so that means when we apply unitarily similarity transformation on B, we get A. So if we perturb B slightly, then the resulting perturbation in A is actually of the same magnitude. That means the change in A is exactly same magnitude of the change in B. So what I'm saying is that if suppose B is replaced by, let's say B is replaced now by delta B. So I have changed B slightly. So this delta B shows the change in B, or you can say the perturbation in B. And then you look at the same thing, U star U. And suppose that this results in the change of A, and the change in A is denoted by delta A. Now clearly you can see that this implies, so what does imply? This implies that delta A is equal to U star delta B U, because A is equal to U star B U. But then this implies that norm of delta A is same as norm of delta B. So this norm is some unitarily invariant norm. You can say the two norm here. So you can say that this implies that any error that a matrix may contain will not be amplified by you can say subsequent unitarily similarity transformation. So any error which was there in the matrix, that will not be amplified by using or by the use of this unitarily similarity transformation. But the same thing cannot be said for an arbitrarily similarity transformation. Why that is? So what I'm saying, so let me write this just for your record. So what you can say from here, so you can conclude from here is that this implies that any error that a matrix may contain will not be amplified by subsequent unitarily similarity transformation. But the same thing, as I mentioned, the same cannot be said. The same cannot be said of arbitrary similarity transformation. Arbitrary similarity transformation means when U is just an invertible matrix. Why that is? So let us look at this example. For example, just to convince you more on this, you can look at this example. So let's look at this 2 by 2 example where S is this matrix, okay, where alpha is some real parameter, okay, and you consider your matrix, let's say A as 2001. So I'll give you 2 examples. So let us look at this first example with the same S. Okay. And you apply this similarity, use this S matrix for the standard similarity transformation. That means you just do this S inverse AS, and suppose that this is the matrix B. Okay. So what is B? So you just apply S inverse, you multiply S inverse A and S. So what you will get is this matrix 2 alpha 0 1. This would be your B. Now you can clearly see that if you look at the, let's say for example, infinity norm of A, what is the infinity norm of A? It is just 2, right? But what is the infinity norm of B? This can be made arbitrarily large by choosing this alpha. By choosing alpha arbitrarily large, we can make this infinity norm of B as arbitrarily large. But similar thing can be said for 2 norm also. Same way. So here I use this infinity norm just to show you that, because infinity norm is easy to compute here. But in fact, if you just look at some other norm, then it would be like it would be difficult to like find that norm. But it's the same thing can be said for that also. So for the example, similar thing you can say for 2 norm also. So what I'm saying is that this B in norm of B, this can be made arbitrary large. Or similar thing you can say with respect to 2 norm also. So now you can see that here the matrix A is like well conditioned, but or you can say if the whatever be the norm of A, if you look at the norm of B in comparative to norm of A, it's very different. In fact, by choosing alpha large enough, you can make this B arbitrarily large, norm of this. So the norm is not preserved, and therefore the error is also not preserved. That means if you change if you change A slightly, the change in B may be like arbitrarily large. For example, you look at here. Let us consider this matrix A, which is the diagonal matrix, just the identity matrix of size 2 cross 2. And suppose that you change your matrix slightly. So that means take this epsilon and suppose that, so it's the, you have changed your the entries of A slightly. So this is the change in A. So let's say delta A. Okay. So that means if you just look at the relative error, that means if you look at this ratio, then it is just epsilon. Okay. Where this, so as I, so this is operator infinity norm. So it is basically this norm in our notation. So this is epsilon. But if you look at now, so you can say that the change in A is very small. If epsilon is small, then change in A is very small. So if epsilon, let's say, it's close to 0, so you have changed entries of A slightly, so not much. Okay. Now, if you look at the matrix B, which is obtained by doing this perturbation or applying this similarity transformation, and when you change the matrix A slightly, then suppose that the change in B is denoted by delta B. Now, if you again look at the, so what it will be, it would be like delta B equal to S inverse delta A S. Now, if you look at this delta, this relative error now, if you look at this relative error, this depends on alpha again. So this can be made arbitrarily large by taking alpha large. So this can be made arbitrarily large by taking alpha large. Okay. So now you can see that at least that what you have already realized, or at least you have some feeling that if you apply unitarily similarity transformation over the standard similarity transformation, then you achieve more, like because of the properties of a unitary matrix, the error is not amplified, and also the calculation of inverse and then the other properties of unitary matrix you can utilize, and things can be made, like they can be simplified and can be made computationally easy. Okay. And this is the advantage of having like unitarily similarity transformation over just standard similarity transformation. So now in the following, now whatever I will talk about, at least up to some extent, before introducing Jordan canonical form, before that we will talk everything about unitarily similarity transformation. So I will mention that, but only for Jordan canonical form we will say that a matrix is similar to some Jordan form. But before that, all the factorization I will say with respect to like where the unitary matrix is involved. Okay, so let me just recall a few more properties of unitary matrix. I will just list them here. You can verify these properties yourself. We have done this before also, or you have done it in some other course. So suppose that you have a matrix U of size n cross n. Then the following are equivalent. All these whatever I'm writing now, they are equivalent. That means U is unitary. This is equivalent to saying that U is non-singular. That means invertible, non-singular or invertible, whatever you want to use, invertible. And U star is U inverse, the same thing. Or you can say that, so we have defined unitary matrix by the property that U star U is identity, but it is same as U star is identity. You can say that instead of U is unitary if and only if U star is unitary. That is also true. So U star is unitary. Or you can say that U is unitary if and only if the columns of U columns of U form an orthonormal set. And similarly, you can say U is unitary if the rows of A or rows of U form an orthonormal set. So the columns or rows, they form an orthonormal set for a unitary matrix. Similarly, you can say that if the length of every vector, that means with respect to the standard product, inner product, if this is equal to this for every vector x in Cn, then it is unitary. So all these properties are equivalent and they are standard properties for a unitary matrix. So I'm not going to prove them. They are very easy also. So you can do it yourself. So the proof I will leave as an exercise, because it is already done in some other course. Okay. Not only this, there are some other properties also. Like if you look at the subset of or you look at the collection of all unitary matrices, or you talk about set of all unitary matrices in this space, that means if you look at, or you can, let's say you can make an observation here. So if suppose this is the set of all complex matrices of size n cross n, this is the set of all invertible matrices of size n cross n. Okay, so this is the set of all non-singular matrices. So this is the standard notation for this set. This is called GLNC, group of all. So this set forms a group. So this is the group notation for this. The group of all non-singular matrices of size n cross n under multiplication. Okay. So now if you look at the set of all unitary matrices, let me denote it by this. What is this? This is the subset of these, because unitary matrices are invertible. So every unitary matrix is invertible, but not every invertible matrix is unitary. So this is the set of unitary matrices of size n cross n. Now you can verify that this set is actually a subgroup. So if you look at GLNC as a group, then this is a subgroup of this. So this forms a group. So this set of unitary matrices has a group structure on it under multiplication. Okay, so this is a group. So this forms a subgroup of this. Okay, the second observation, if you look at the set here, the set of unitary matrices, then, and if you look at this space of matrices with respect to some norm, or together with some norm on this space, and if you look at the topology which is defined by that norm, then this set of unitary matrices, this is a compact set. This is a closed and bounded set in this space of all matrices. So this is closed and bounded, and therefore you can say that the set, or you can say the group here of unitary matrices is compact in this. Why this is compact? Because it is closed and bounded. Why this is bounded first? So why this is bounded? It's very easy to see why this is bounded. Because so for example, if you look at, so all the norms are in the finite. So this is finite dimensional space, and all the norms are equivalent. So you can take, let's say for simplicity, operator 2 norm, and then what is the 2 norm of U? It is 1. So what does it mean? It means that all the entries, the absolute of each entry of this matrix U is less than equal to 1. This is for all ij. So clearly you can say that this set is bounded. Okay. And why this is closed? Why this is closed? So if you take any, let's say any sequence of unitary matrices, that convergent sequence of unitary matrices. So let's say UK is any sequence of unitary matrices that converges to a matrix U. So let's say these are unitary. Now if you show that this U is also convergent or U is also unitary, then you can say that this is closed, this set is closed. So if UK is a sequence of unitary matrices, and suppose that this UK converges to U. So if you show that U is unitary, then that means that this set is closed. Right? Now, you know that UK is unitary. So what does it mean? It means that UK star UK is identity for all K. Right? Now, what would be the limit of UK star UK? Because UK is a convergent sequence, UK converges to U. So the limit would be U star U. But then what is this actually, the left hand side? For each K, you know that UK star UK is just identity. So it is, the left hand side is identity. So this implies that U star U is identity. So this implies U is unitary. So this set is closed. So the set of unitary matrices forms a, or is a compact set in the space of matrices. All right, so these are some properties of unitary matrices or the set of unitary matrices, and you have already seen why we have certain advantages when we apply unitarily similarity transformation. So now I will define this formally. What is unitarily? What do I mean by unitarily similar or unitarily equivalence matrices? Unitary equivalent matrices. So what is a unitary similar or unitary equivalent matrices? So a matrix B is said to be unitary similar, or you can say unitary equivalent, both are same, equivalent to a matrix A if there exists a unitary matrix U the same size such that B is equal to U star A. Okay, so if A is similar to B via a unitary matrix, then it is called, then they are called unitarily similar, or you can say unitarily equivalent. Okay. Now, as we have seen, or at the beginning, I mentioned that if we have a complex matrix of size n cross n, then it is always similar to an upper triangular matrix. So there I did not mention unitary similar, but in fact you can say that every matrix is every complex matrix of size n cross n is similar to an upper triangular matrix via unitarily similarity transformation. That is the Schur's lemma. We will prove next. But let me just tell you that one thing here. Clearly, via this definition, one thing is very clear, that unitarily similar or unitary similar implies similar. So if two matrices are unitary similar, then they are similar also. But the converse is not true. Converse is not true. So this is not in general true. Why this is? Because I can give you one example here. So if you take these two matrices, let's say A and B, then A and B are similar You can verify that A and B are similar, but they are not unitarily similar. Why this is? Because if you look at the, you know that if A and B are two matrices which are similar, then their Frobenius norm is same, right? But you compute the Frobenius norm of A here and Frobenius norm of B. If they are similar, then their norm has to be same. Frobenius norm has to be same, but they are not same. So therefore, this is, they are not unitarily similar. So they are similar but not unitarily similar. Now, before I move further, can you tell me when we, I forgot to ask you at the beginning. So when we say that two matrices are similar, what do by this, what do we mean? So what do we mean by saying that two matrices are similar? Of course, we know that the definition is there, that there exists an invertible matrix such that S inverse A, S is equal to B. But in other words, you can say that the B matrix is actually a representation of A in a different coordinate system. This S matrix actually it gives you it gives you a different coordinate system. It's like a change of basis, you can say. So B is like a different representation of A in a in a different coordinate system. So A has A is one representation with respect to one coordinate system, and S inverse AS is actually a matrix of A in a, or the same matrix A in a different coordinate system. So it's like a change of coordinate system, or you can say it's like a change of basis from one basis to another basis. Or you can say that if you look at your matrix as a linear transformation, then A is the matrix of linear transformation with respect to one basis, and B is the matrix of linear transformation with respect to some basis, some other basis. And this S matrix is actually the change of basis matrix, right? But here, in case of unitarily similar, we have the same thing, but the basis is different. Can you tell me which basis it is? So what can we say when we, if I want to make similar statement for unitarily similar matrices also, then what can you say about this? So can you see B and A also as change of basis, or this U as a change of basis matrix when you convert like B?
So your screen is not visible.
Not visible?
No, sir. Yes, and now it is.
It's visible now. So since when it was not visible?
The last 30 seconds, I guess. 30 or
30
1 minute.
seconds. Okay, so 30 seconds is fine. Yes. So the question is, when I say two matrices are similar, that means we are looking at these matrices in different coordinate system. When you look at two unitarily similar matrices, you can say the same thing. But then unitarily equivalence or unitarily similar matrices, they are like similarity, but it is like a special type of change of basis. So it is like a change from one orthonormal basis to another. Okay. Now orthonormal basis has an advantage over like a standard basis, because in orthonormal basis, when you in orthonormal basis, there are certain things which are unchanged, like the sum of squares of the absolute values of the entries. That means the two norm, basically the Frobenius norm, it doesn't get changed with respect to the Frobenius, with respect to the orthonormal change of basis. But in the usual change of basis, it is changed. It is not the same thing. So it is a different kind of like change of basis. It's a or one change of basis from one orthonormal, it's a change of one orthonormal from one orthonormal basis to another orthonormal basis. So if you look at these two matrices, or if you look at this matrix as a linear transformation, then you can say that A is the matrix representation of that linear transformation with respect to one orthonormal basis, and B is the matrix representation with respect to a different orthonormal basis. And this U matrix is actually the change of orthonormal basis matrix. Okay. Anyways, it's not important. You just know this thing also. So as I mentioned that every matrix now, we will prove the next thing is the Schur's lemma, or the Schur's decomposition also is the standard thing, standard term used for this result. It is called Schur's lemma, and sometimes it is also known as Schur's decomposition. So what it says that if we have a matrix A over C, it's a square matrix over C, then it can be upper triangularized by a unitary matrix. That means it is unitarily similar to an upper triangular matrix. Not only that, we have some freedom to choose the diagonal entries of this upper triangular matrix. So let me first write what it says, and then we will see how powerful this result is. It gives us many other results. So it is called Schur's lemma. So suppose that we have a matrix A of size n cross n. Okay. And suppose that lambda 1, lambda 2, these are lambda n, these are the eigenvalues of A. Okay. So we have a matrix A, and we also have eigenvalues of A. They are in some prescribed order. Like when I said lambda 1, lambda 2, and lambda n, that means I have ordered them in some, I have arranged them in some order. Okay. Then there exists then this result says that there exists a unitary matrix U of the same size such that U star AU is equal to T, where T is upper triangular. Upper triangular. So if I, let's say, if I denote the entries of T by Tij, then this result says that there exists a matrix, unitary matrix U, such that U star AU is T with Tii is equal to lambda I. That means the ith diagonal entry of this upper triangular matrix is nothing but lambda I for each I equal to 1 to n. Okay. All right. So let's see why this result is true. So I'll quickly give you some idea how to prove this. I won't prove it completely because you will understand how to prove this with two steps. So what is given to us? We are given a matrix A. So this is given to us. And what are given? We are given the eigenvalues also. These eigenvalues are also given. Okay. So suppose that, so we need to construct this U such that U star AU is upper triangular, where the diagonal entries of the triangular matrix is nothing but lambda I. Okay, so I will start with the first eigenvalue. I will do it in like finite number of steps. Okay, I will construct this U matrix in a finite number of steps. So let us see how to do this. So lambda 1 is an eigenvalue, so I will take a eigenvector x1 non-zero. So it's a non-zero vector in Cn. So let x1 be a non-zero vector such that ax1 is equal to lambda 1 x1. So it's a eigenvector corresponding to eigenvalue lambda 1. And I'm assuming that the 2 norm of x is 1. Okay, so it's the operator 2 norm, which is, or it is, the 2 norm is actually, when I don't mention anything, it is actually the norm which is induced by the inner product. That means this is this norm x star x, square root of x star x. This is the standard thing. All right. So we can choose x1 eigenvector corresponding to lambda1, such that 2 norm of x is 1. And then what I can do here, I will choose y2, y3 and yn such that this x1, y2 and so on yn, this forms an orthonormal basis of Cn. So can you tell me why this is possible? Can I always do this? Can I extend this x1 to an orthonormal basis basis of Cn? If yes, how to do that? How to get this y2 to yn such that this becomes an orthonormal basis? So can you tell me how to extend this x1 to an orthonormal basis of Cn?
So since x1 is non-zero, it's linearly independent, so can be extended to a basis, and then from Gram's matrices
Yes.
can be converted to
Exactly. Yeah, good. So you can use you can first extend this x1 to a basis and then apply Gram-Smith. So without loss of generality, we can write it that there exists y2 to yn such that this becomes an orthonormal basis. All right. Then I can set u1 as, so I will construct this u1. It's a matrix where the columns are nothing but x1. The first column is x1, the second column is y2, then y3 and so on up to yn. So clearly this u1 is an n cross n matrix. And also since the columns are orthonormal, this u1 is unitary. Right? And if you look at what is AU1, AU1 is when you multiply AU1 column wise, the first column would be AX1, the second column would be AY2, then AY3, and so on up to AYN. It's the same thing. It's the multiplication of A with U1. But we know AX1 is just lambda1 x1. Okay. So now if I apply U1 star from left hand side, so what is U1 star? It is U1 star would be x1 star, the first row, the second row would be y2 star, and so on up to yn star. And then AU1 is lambda1 x1, AY2, and so on to AYN. So can you tell me what would be the first column here? The first column of this product. So what would be the first column of this product here? Product of this matrix and this matrix here. So what would be the 1 entry here? It would be lambda x1 when you multiply x1 star. So you have to, how would you multiply these two matrices? The x1 star would be multiplied first this. So this is the 1 entry. So 1 entry would be lambda1 x1 star x1, but x1 star x1 is 1 because norm of x1 is, sorry, norm of x1 is 1. So this is just lambda1. But then the second entry, the 2 entry here in the first column, it would be lambda1 times y2 star x1, but y2 and x1 are orthonormal, so it would be 0, and so on. The other entries would be 0. So this would be the first column. The other columns we don't know yet, so there would be some entries in the first row after 2 to n, and this would be some n-1 cross n-1 matrix. So I'm calling this A1. So at least you can see now the first column I have like created zeros in the first column. So it is in the form of an upper triangular matrix. So whatever I did now for A, I will do the same thing for A1 also. So now let us look at the second step. So then you can see then this matrix A1 is of size n-1 cross n-1. So A1 is of size, it's a smaller size now, n minus 1 cross n minus 1, and also eigenvalues of A1. So can you tell me what would be the eigenvalues of A1?
So lambda 2, lambda 3, and so on.
Why?
Because these two matrices are similar, and lambda 1 is one eigenvalue, then remaining eigenvalues will be remaining eigenvalues.
Lambda 2 to lambda n, yes. So basically the eigenvalues here, eigenvalues of this matrix are nothing but eigenvalues of this here, this matrix, and eigenvalues of this matrix, the union of these two. But eigenvalues of this is just one, this is just one entry, so lambda 1, and these are the remaining eigenvalue. But we know that the eigenvalues are given by lambda 1 to lambda n. So eigenvalues of A1 are nothing but, so A1 are lambda 2 to lambda n. So what I will do now, so I'll do exactly the same thing. Whatever I did for A, I'll do A1. So what I will do, I will choose x2, which is non-zero. It would be in Cn minus 1, such that A1 x2 is equal to lambda 2 x2, and norm of x2 is equal to 1. Okay. So do exactly the same thing and find a matrix U2. So do it all over again and find a matrix U2 of size n minus 1 cross n minus 1. Find unitary matrix of this size such that U2 star A1 U2 is of the form lambda 2 star 0, and then there would be a matrix A2 of size n minus 2 cross n minus 2. Right? But then our aim is to construct or convert matrix A in an upper triangular form. So here A1 is of smaller size. So we should construct a matrix. Let me we should construct a we should use this information here, whatever we did, in order to construct an unitary matrix, so that we can introduce the second column in our upper triangular matrix for matrix A. So what I would do here, I would set a matrix using this U2. I would set to V2, let's say, of this form. The first entry is 1, 1 entry is 1, other entries in the row are 0, and also in the column, first column are 0, and then U2, this matrix here. Now this is n cross n because U2 is of size n minus 1 cross n minus 1. So this is n cross n. So this is n cross n, and also V2 is unitary. The columns of V2, you can check that the columns of V2 are orthonormal because U2 is orthonormal or U2 is unitary. So this V2 is n cross n unitary matrix. Okay. And now if you apply V2 on this matrix U1 star A U1. So you remember what was U1 star A U1? So V2 is this one. This is V2 star. U1 star A U1 is nothing but this one, lambda 1, 0, 0, A1. And then V2 is 1, 0, 0, U2. So if you multiply this, then what you will get? You will get lambda 1, lambda 2, and then there would be some matrix here, and this would be A2. Okay. Now you can see that you have obtained the second column in your upper triangular matrix. Now if you keep on doing the same thing, so if you continue the process, then after like n minus 1 step, so you can see that continuing this process will give you unitary matrices. Let's say V3, V4 and up to Vn minus 1 such that this matrix, so V1, V2 and up to Vn minus 1, this matrix is in the desired form. It's lambda 1, lambda 2 and so on up to lambda n, and then we have this upper triangular form. So this is your matrix T. And since you know that the product of unitary matrices is again unitary, so now you can collectively call this product as U. So this would be U star. So you have constructed a unitary matrix U such that U star AU is upper triangular, where the diagonal entries are nothing but coming in the right order. Okay. So now this result is nice because this is achieved by unitary similarity transformation, and this is actually the main idea of eigenvalue computation algorithm. That means if you have a matrix A, then this Schur's lemma says that there exists a unitary matrix U such that U star AU is upper triangular. This is the theoretical result. Okay, but it gives us a hope now to generate or to find iterations, like iteratively achieve this decomposition. That means, can we convert our matrix A iteratively into an like upper triangular matrix, or a matrix which is in almost upper triangular form. That means the entries which are appearing here in the lower part, they are of small magnitude, they are close to 0. So this is actually the main idea behind eigenvalue computation algorithm, where these similarity transformations are like obtained iteratively in order to convert this matrix A into an upper triangular matrix, and then the diagonal entries of this upper triangular matrix, they give the eigenvalues. Okay? So this is the result which is used in eigenvalue computation, but we'll discuss this also in some more detail. But before this, let me give you two kind of unitary matrices which are actually very useful in applications. So for example, if I give you these two matrices, unitary matrices, then if you use these matrices for your similarity transformation, then you can achieve like many things for your matrix. So for example, let me first give you these examples. These transformations have a name. They are called householder transformations. So let me give you examples. What are these transformations? These are called householder transformations. So householder transformations are actually unitarily similar transformation, but that unitary matrix has a particular form. It is either behaves like a rotator, like a rotation matrix, or like a reflection matrix. So in R2, you know what is rotator or reflector. They are like linear transformations. I'll give you example. But in general, Rn also or Cn also, you can talk about these rotators and reflectors. And they have, if you use them for your similarity transformation, then that transformation is called householder transformation. So the first example is, so there are two kind of matrices, unitary matrices. The first one is the householder rotators. So they have different names. So they are called either plane rotators or like Given's rotator or householder rotators. There are different names for it. So what is this? So for example, for a 2 by 2 matrix, let us look at the 2 by 2 case. So in R2, let's say, you know what is a rotation matrix. So if suppose you want to rotate a vector with an angle theta, then you can do it by using rotation matrix. So that means if you choose this Q matrix, let's say cos theta minus sine theta, and cos theta. Right. So when you apply this Q star or Q transpose on a vector xy, then the resultant vector, so let's say x1, x2, then the resultant vector y1, y2 would be a rotation of this vector x here with an angle theta. Okay, so this is the rotation in xy plane. But you can generalize this idea and similarly define this rotation for n-dimensional plane also, or n-dimensional space also. You can verify that this Q matrix here, this is a unitary matrix, or you can say real orthogonal in R2. It's a unitary matrix here. So let me define this here in general by using the same idea. So this is the notation I will use. So it is like you can say the rotation through an angle theta in the plane, in the ij coordinate plane. So that means if suppose you have a vector this x1 to xn and you just want to have a rotation in the first two entries, that means the 1 and 2. So I equal to 1 and 2. You can choose this accordingly, and then you can decide this matrix U, and that the resultant vector would be like rotation in only 1 and 2 plane. It won't affect or it won't change anything in the other entries. So this is what I mean by that. So it's the matrix that that carries out a rotation through an angle theta in the ij complex plane. So what is this matrix? It is basically, what you do is that you put this rotation matrix, the 2 by 2 matrix, whatever I just mentioned, that matrix you put in the ith row and ijth row and ijth column. So what I'm saying is the following, that you put this matrix, rotation matrix, at an appropriate place, and the diagonal entries are all 1. Okay, so these are 1 except this cos theta at the diagonal, and then you have this. So these diagonal entries are 1, and then the other entries here are 0. So this is the ith column. This is the jth column. It has a similar structure. All the other entries are 0. And here similarly you have for this also. This is the ith row, and this is the jth row. Okay, so all the other entries are 0 here. So what I have done here, let me use a different color. It is cos theta here, then minus sine theta, cos theta. Okay. Now what is this matrix? So this is the ith column, this is the jth column, and this is ith row, and this is jth row. Okay. So what is this matrix? You can verify that this matrix, this is a n cross n matrix, and this is a unitary matrix. So this is a unitary matrix. This is, or when everything is real, then it is a real matrix. It's a real orthogonal matrix. In this, for any given theta, or for any I and j, where I is less than j, and any theta, angle theta between 0 to 2 pi. This is an orthogonal matrix, the first thing. The second thing is that this, when you apply this on a vector, then it simply carries out, uh, is out a rotation throw an angle. Throw an angle theta, and this rotation is only in the ij coordinate plane. In the ij coordinate plane. So if you look at again carefully, since this is the identity matrix, so it's the identity matrix. The only thing is that at the ith row and jth row and ijth column, you have inserted this rotation 2 by 2 rotation matrix. Otherwise, it was an identity matrix. Okay. So when you apply this u on a matrix from left hand side, then it will only change ith and jth row of the matrix. And if you apply u from right hand side, it will only change ith and jth column, and the other entries of the matrix would remain same. So what I'm saying, that left multiplication, if you do left multiplication by this matrix u, then my left multiplication affects only row I and j, and similarly right multiplication affects only columns I and j. Okay, so the only two rows and two columns would change if you apply this similarity transformation. So when you do like u star a u, so you multiply u star from left hand side and u from right hand side, then the left multiplication would change only two rows of a, and the right multiplication of u would change only two columns, that means the ijth columns, and the other entries of a would remain same. Okay, so this matrix is called plane rotators or Gibbons rotator. The second matrix, I'll show you why these matrices are useful and they are of particular importance for us. But let us first define the second matrix also. The second matrix, it is called the Householder reflector. Householder reflectors. So it will behave like a reflection on like one-dimensional surface space. So how it is defined? Suppose that we have a vector w in Cn which is not zero. Okay, and based on this vector w, any vector non-zero vector w, I will define a matrix. Let's say uw. What is how it is defined? It is just the identity matrix minus t times w star, where t is 2 times w star w. Now you can see here this w star, this is an n by n matrix because w is a column vector, so it is of size n cross 1, and w star is of size 1 cross n, so this is an n cross n matrix. So uw is an n cross n matrix, and w star w, this is a 1 cross 1 matrix, that means it's a scalar. Okay, so t is twice of w star w. Okay, so in particular, if 2 norm of w is 1, then w star w is 1, so t equal to 2. So in that case, you can write that uw is just I minus 2 times w star. Right? Now again, for this matrix also, you can verify that this uw, this is a unitary matrix. For any w, if you look at this uw, this is a unitary matrix, and you can verify that if I apply what is uwx, so you can say that if I take any x which is in the orthogonal complement of w, that means for any x such that x is orthogonal to w, what would be uwx? What would be uwx? Can you tell me? When I apply x on this uw from right hand side, what it is? What is this? So here is your UW. So when you apply X on this UW, then what do you get? So if I apply, yes. So what is UWX?
X.
It is just X because it is I minus T times WW star. You apply X from right hand side, so it would be just X because W and X are perpendicular. So you can say that this UW acts as the identity matrix on the complement of U, complement subspace W orthogonal complement, right? Similarly, if you apply W on this UW, what do you get then? If you apply W on UW, then what do you get? You get minus W. So that means this UW acts as a reflection on the one dimensional subspace, spanned by W. Okay. So these two matrices, as I mentioned here, Raoult-Solder reflectors and rotators, they have they are very important in like, for example, in eigenvalue computation algorithm, or suppose that you want to create zeros in a matrix. So as I mentioned when I discussed Shor's lemma, I said that this Shor's lemma is useful in eigenvalue computation algorithm because this result says that every matrix A is unitarily similar to an upper triangular matrix. Okay, but how to find this U? That is the thing. So I have told you how to do that. In the proof of Shor's lemma, you can see that there is a way to create zeros, but that was in theory. But practically also, what you can do, you can start. So if suppose A is this matrix, has n columns, then what you can do, you first look at the first column here, first column of A, and then try to create zeros by, so that means you try to multiply, let's say Q1 some matrix Q1 on A from left hand side, and similarly for right hand side to preserve the similarity transformation, and do like something like this, and then here you have some matrix. Okay, so that means you create zeros in the first column. Then in the second step, what you do, you again try to find Q2 such that when you apply Q2 on this matrix, you create zeros in the second column, and you should do it in such a way, and then there are these rows, and then we have some matrix here. So you should do it in such a way that the zeros which are created already, they are not disturbed when you apply Q2. Similarly, you keep on doing the same thing and you try to convert your matrix into an upper triangular matrix. Now you can see that all these Q1, Q2, they are unitary matrices. So basically their product is again unitary. So eigenvalues of A are nothing but eigenvalues of this upper triangular matrix, and you can easily read the eigenvalues of this upper triangular matrix. So this is the idea. This is not exactly the algorithm, but this is the idea to like find the eigenvalues of a matrix. Now, as I mentioned, the one important step here is to create zeros in a matrix. That means you can see here, if I need to, the important thing is to find this Q1 such that Q1 star A Q1 gives me zeros. Or you can say that, okay, you try to find Q1 such that q1 star x, x is let's say the first column of A, and then you want to have a y as of this form. First entry is not 0 and the other entries are 0. Okay. So this is you want, and whatever matrices I have defined here, these two matrices, the householder rotators and reflectors, they can be used to achieve this. Okay. So for example, let me show you how you can do that. So for example, so let us see the rotators first. So as I mentioned, the rotators you can use to create zeros in a vector or a matrix. So this is one of the most important thing to like achieve several decomposition for a matrix using unitary similarity transformation. How? So how you can use this? So rotators can be used. So first I will show for rotator and then we will see for reflectors. So rotators can be used to create zeros in a vector or a matrix. How you can do that? So for example, suppose that we have a vector x and x2, and assume that x2 is not 0, because if x2 is 0, then there is nothing to do. So let us understand this in 2 by 2 example, with a 2 by 2 example. So suppose that x is of the form x1, x2, and suppose x2 is not 0, because if x2 is 0, then there is nothing to prove. And then we want to find q, reflector or rotator, sorry. We want to find rotator q, that means cos theta minus sin theta, cos theta. We want to find this rotator q. So in our notation, what it is theta 1, 2. Okay. Such that we want this q such that when I apply q transpose on x from left hand side, I get a vector of the form y0 for some y in R. So I want to create 0 in x. That means when I multiply q transpose from left hand side, I should get a vector of this form. So I'm trying to create zeros in a vector using a rotator. So let us see how to find such a q. So the main thing is that we need to find theta so that we can achieve this. If we know theta, then we know this q. So that you can decide from here. So let us see what is q transpose x. What is q transpose x? Q transpose x is cos theta minus sin theta, cos theta, and x is x1, x2. So basically what it is cos theta x1 plus, or you can say x1 cos theta, x2 sin theta, minus x1 sin theta plus x2 cos theta. And this vector is actually equal to, we want this to be equal to some vector y of the form y0, okay, for some y. So from here, to achieve this, you can say that this can be achieved provided this theta satisfies this thing. So this is true if and only if you can say if x1 sin theta, because of the second equation here, x1 sin theta is equal to x2 cos theta, or this is equivalent to saying that tan, so this tan theta is equal to x2 x1, or you can say theta is equal to tan inverse of x2 by x1. So from here you can find this theta, and then you can substitute this theta in q, and this would be the matrix q that gives you that creates 0 in this vector x. Now this is a 2 by 2 example, but then if suppose let's say you have a n by 1 vector x, then what you will do, if suppose you have x1, x2 and so on up to xn. So first you apply a rotator of this form with an angle theta and on 1, 2 coordinate plane, then this will create 0 here, right, in the second entry. Then you apply So you apply this one, then you apply q theta on 1 3. Then it will, because when you, as I mentioned, when you multiply this rotator from left hand side, it will only uh, disturb ith and jth row. So in the first multiplication here, it will only disturb 1 and 2 rows, so it will create 0 here. But then when you multiply q13 on this one here, then it will create 0 here. And if you keep on doing this, so with an n minus 1 rotators, the use of with use of n minus 1 rotators, you can actually create zeros, or you can make this vector in this form. Right? So you can create zeros using this matrix, unitary matrix Q. So this also gives you a way. So this is for a vector, but similarly you can create zeros in a matrix also. How to do that? So similarly you can do. So similarly we can use rotators to create zeros in a matrix. Right? For example, let's say we have this A. This is our matrix A. If I apply, let's say the first rotator, let's say Q1, okay, or let's say a rotator Q to make A210. So I can do that using the above idea. I will construct a rotator that creates that apply. So what I will do, I will construct a rotator Q transpose or Q, which when I apply Q transpose on A11, A21, then it will give me something like R110 kind of thing. So it is the first entry R11 and then this 0. Okay. And now when I apply Q transpose on A, then what it would be? It would be like R11 because it will apply on the first column. The second entry in the first column would be 0. And then there would be 2 more entries. It would be, let's say, 1, 2 and R22. There would be, the entries would change, but it would be in this form. So now you can see that you can create zeros using a rotator in a matrix also. If the matrix is of higher dimension, you can apply more than one rotation and you can create zeros wherever you want because of the choice of this rotator. If you choose I and J appropriately and this angle theta, then you can create zeros in a matrix wherever you want. Okay. This also gives us a motivation. You can see Q is so this is a upper triangular matrix R. So this is, although it's a 2 by 2 example, but it gives you a nice decomposition here. You can see this matrix A is of 2 by 2. You applied Q, which is an unitary matrix or orthogonal matrix. When you apply this Q transpose from left hand side, then it gives you a upper triangular matrix. So in other words, when you apply Q from left hand side, it would be A equal to QR. So this is same as A equal to QR. So this also gives you a decomposition, or at least it tells you that a matrix it is possible to decompose a matrix into 2 factors, where one is orthogonal and one is upper triangular. So this also tells you something like, or a decomposition of the form QR. So actually this decomposition is known as QR decomposition. So I have not, I'm not defining it here, but I'm saying that you can see that these rotators can be used to achieve a decomposition of the form QR, where Q is orthogonal and R is upper triangular. And in fact, you will see that every n-cross n matrix you can decompose using rotators or reflectors in terms of these 2 factors Q and R. So this is called QR decomposition. We will see this, but at least you can see from here also for 2 by 2, it is very immediate to see. Not only this, if you have this kind of thing, these rotators, they can be used to solve a system of equations also. Like if you have, let's say, AX equal to B, then from here you can see when you apply Q transpose from left hand side, so assume that A is, so you have this decomposition A equal to QR. So when you apply Q transpose from left hand side, then it would be Q transpose B. So now what you can do in solving system of equation, first you define C, which is Q transpose B. Once you have this C, then you can solve this Q transpose A is just R then, because A equal to QR. So then you solve Rx equal to C. So this system of equation you can solve in two steps. First, provided you know this A equal to QR, which you can achieve using the rotators. So first you solve, first you obtain this product Q transpose B, call it as C. And in the second step, you solve this upper triangular system, which is easy. You know how to solve an upper triangular system by a back substitution. So you can do this also. You can use this idea in order to solve a system of equation. All right. So this is again, you can see a different application or different use of this. Similarly, you can use reflectors also. Reflectors, when you apply on a matrix, it will disturb all the, or it will change all the entries of a matrix. Unlike rotators, where the rotators only, when you apply from left hand side, it will only change ith row and jth row and I and jth column when you apply from right hand side, right? But in case of rotators, when you apply from left hand side, it will change all the rows, and when you apply right hand side from right hand side, it will change all the columns. But the advantage is that if suppose you have a n by n n cross n vector, and if you want to create zeros here, if you want to have, let's say, this kind of vector using the rotators, then you will have to apply n minus 1 rotators, and then you will get this. But in case of reflector, if you just apply one reflector here, then I will show you how to do that. Then when you apply on this, then in using one reflector itself, you will get a vector which is in this form. And therefore reflectors are also they are also you can say more useful in creating zeros. Okay, so I have already discussed something, at least some things about rotators, but similarly you can use reflectors also. So I don't have much time, so I'll just I state one thing here first. So let me give you this as an exercise so that you can try yourself also. So suppose that we have X in Rn with, let's say, okay, so let's say X is in Rn, and let us assume that we have a vector Y is also in Rn such that Y is not equal to X. Okay, so we have two vectors X and Y which are different. Then find or it is possible to find a reflector or householder reflector. Householder reflector, can say UW, such that when you apply UW on X, you will get Y. So that means you can go from one vector to other vector by an application of this householder reflector. And this is true for any vector X and Y such that the vectors are different. So in order to construct such a reflector, what you need to do here? So in the definition of reflector, you just need to know this, choose this vector W. If you know this, if you choose W appropriately, then UW is very easy to construct, right? So the main thing is to see what is W. So if you choose this W accordingly, then you can achieve this. So I can give you this hint. So you try with this W. where W is X minus Y. Okay. So basically idea is that what is given, so you can understand this way also. If we are given two vectors X and one vector is Y. So we want to get this Y when we apply a reflector on X. So basically we want Y to be a reflection of X, and this reflection is with respect to this one dimensional space here. So this is W. Yeah, so this with respect to this space. So W is a vector which is orthogonal to this space. So basically if you look at this vector here, which is so this is a bisector of the angle between X and Y, and this vector is actually X minus Y. So what you can do, if you choose W as X minus Y, then you know what is the property of UW. You will get this UW, and when you apply this UW on this, then you will get, so basically when you simplify, construct this UW and verify, then you will know that this UW sends X to Y. Basically you can verify this. So so the idea is that you choose W in this, and then you construct your UW, and then you can verify whether it is satisfying this thing or not by seeing that X, by writing X in this form, X minus Y plus X plus Y. So you can write X in this way, and then you can verify that this effect. Now in particular, what you can do here, in particular, so now you can use this reflector to create zeros. Why? Because in particular, if you choose, let's say Y, so let's say X is of this form, X1 to Xn, and let's say Y is of this form, star and 0, 0, 0. Okay. Then from this result, you know that there exists a reflector UW such that this UW sends X to Y. That means it creates zeros in X. Okay, and that this also gives you an idea to create zeros in a matrix. So this is basically the main idea, or that means the creating zeros to convert a matrix into a simpler form, so that and in a like in a unitarily similarity transformation preserving way. That means you preserve all the properties which are preserved by similarity transformation, unitarily similarity transformation. Okay, so we will continue on this in the next lecture. So it's time, so I'll stop here. If you have any doubt, you can ask. If there is any doubt, you can ask. Otherwise, we'll stop here. All right, so if there is no doubt, then we can stop, and I will see you in the next class.